who is also the HOD of Physics, Dr. Rajendra Rathi sir, Dr. Nana Pradhan sir, Dr. Bhupesh Mude sir, Dr. Pratap Patil sir, and Omkar Ramdasi sir, Dr. Sneha Nandi madam, Mr. Devendra Chavan sir. After an exciting day one presentations, we look forward to day two of our fest. We begin the day with an expert lecture by Omkar Ramdasi sir on X-ray diffraction. Over to Vijay Mahekar sir.
Thank you very much, Krish. Good morning to you. Good morning to Rati sir, Omkar sir, Sneha madam, Devendra sir, and to all my students. Okay, it's my privilege that I am doing introduction to one of our faculty who is the who has recently joined us. He is currently working as an assistant professor at Department of Physics, Ramnandri Autonomous College. He has qualified several exams like CSIR NET exam in December 2018 as well as June 2020 with All India rank 37. And sir has cleared SAT exam in 2018 and GATE exam in 2017. He has completed MPhil and MSc from the Department of Physics, Pune University in 2016 and 14 respectively. He has published several research papers in various national and international journals and has presented his research works at various conferences by posters and oral presentations, which were also acclaimed by various awards. He was invited as an expert to deliver a talk on the NET-SET exam preparation in state and national level workshops. His research interest primarily focuses on material science and lead-free piezoelectric and fuel-electric materials. He is also a reading and traveling enthusiast. With this brief introduction, I request Omkar sir to start the session. Over to Krish sir. Over to Krish.
Sir, so as we begin with our first lecture for the day, our first expert lecture, Omkar sir will be giving us an introduction to scanning electron microscopy and its applications. Omkar sir will be giving us an introduction on X-ray diffraction. So over to Omkar sir.
Okay, thank you, Krish, and Dr. Vijay Mahekar sir, head of the department, and all respected colleagues, Rati sir, Pradhan sir, Mode sir, Dr. Pratap Patil sir, for warm welcome and inviting me for this doing expert lecture on the X-ray diffraction pattern. I'm not that much expert on this technique, but I will try my best to give some of brief idea as we have UG and PG students right now here. So I hope after the lectures that will give the immense little bit of further idea about the research, what is XRD and what are the different applications we can do. So I will start with my presentation. Share my screen. The screen visible? Krish?
Yes, sir.
Yes, sir.
Visible.
Yes, sir. Yes, sir. It is. It is visible.
Oh, okay. Okay. So today, as a part of the second day of our annual physics fest, this time is to be the online physics exhibition fest, that is Infinity 2020-21. So in the second day, yesterday we have got first lecture by Dr. Vasant Sate on the Raman spectroscopy. As sir has mentioned, that is the basically the science day, which is the discovery of the Raman effect. Okay, so for that, in that case, the 20th Feb is declared as a science day. Now today I will try with the different spectroscopy, which is X-ray diffraction. So these are the contents or outline of my presentations are introductions, principle, and I will go to the instrumentation part. Then there are different types of X-ray diffraction methods. I will go with that. And some of the applications and some limitations. Okay. Now, before starting with this, we know that X-rays were discovered by William Röntgen, which is called X-rays. Okay, because whatever rays which are found, those are unknown rays. Okay, so anything which we don't know, we can appear as X. So these are the X-rays which are discovered in 1895 by William Röntgen, and for that he has got first Nobel Prize in Physics in 1901. Okay, and the X-ray diffraction in the crystal was discovered by the Lau. Okay, so all of you are most of the studied the Lau pattern. Okay, which you remember, and the wavelength of the X-rays of these lies in this 0.1 angstrom to 10 angstrom or 10 nanometer. So within that range, so X-rays are used. Now X-rays have short wavelengths depending upon the electromagnetic radiation produced by the de-acceleration of the high energy electrons, and there are different types of X-ray. Okay, so once we have some fracture in our bones, so doctor used to take our X-rays. Okay, so depending upon the energy, okay, so X-rays are categorized in two terms. First one is the hard X-ray and second one is the soft X-ray. So hard X-ray, obviously it has the more energy, it has more penetration power, we can say, and soft X-rays which are less penetrating and having low energy. So depending upon the application or depending upon the bone, okay, on which or which X-ray which you have to take on, depending upon that the energy of the X-ray we can vary. Now X-ray, obviously we know in the electromagnetic spectrum, starting from radio, gamma, microwave, UV, visible, then radio waves, ultrasonics, supersonics. Okay, so the X-rays, we can see that it lies in this 10 raised to minus 10 meter, that is 1 angstrom. Okay, so the range, it lies between 1 to 10 angstrom, and you can see that the frequency, and we know that with going from that radio to X-rays, your wavelength get decrease or energy will increase, and vice versa also we can say. Now the introduction of the X-ray, we can say the X-ray diffraction is a non-contact, non-destructive technique. That is very much important. Whenever we see different types of spectroscopic are there in which you require a sample preparation, like SEM, TM, scanning electron microscopy, transmission electron microscopy. In that case, you have to conduct your sample, okay, with a thin layer coating up to, let's say, 10 nanometer using gold coating or platinum coating, we can say. Now, this is technique which is mostly used to find out or understand the crystalline phases, different polymeric forms, and structural properties of the material. Okay, so any material which you are synthesized, in order to characterize its property, in order to characterize its dimension, in order to characterize its lattice strain or crystallite size. Okay, so I'll go into that one by one. This technique is most widely used. Now, at Nobel's speech, what William Röntgen has said, every crystalline substance gives a pattern. The same substance always gives the same pattern. That is very much important thing. Okay, means let's say if you take an XRD on today or day after tomorrow, it should be same. Okay, it's intrinsic property, we can say, like somewhat resistivity. Okay, so your resistors might change with area and length, but your resistivity, that is intrinsic property, it should be same. And the mixture of substance of each pattern is independent of others. Okay, so depending upon the composition, depending upon the structure, it will be different. And X-ray diffraction pattern of pure substance is like a fingerprint of the substance. So it's same, we can say, as sir has mentioned yesterday about the diamond pattern in the Raman spectroscopy. So at a particular peak, at a particular energy, you are getting a diamond peak. So it's characteristic or intrinsic property of that material. Okay, and the definitions, we can say the atomic planes of the crystal which cause an incident X-ray to interfere with another and they leave the crystal. This phenomena is known as X-ray diffraction. So before going to that diffraction, so as we usually know, in BSc or in 12th also we have studied that diffraction is somewhat the bending of light around the edge of obstacle. Okay, like that. But in case of crystal, whenever you pause X-ray on your particular crystal, the main condition for the diffraction is whatever wavelength you are using, that should be comparable to interplanar spacing. Interplanar spacing means what? The distance between two consecutive planes. So if you see the electromagnetic spectrum, now the interplanar spacing is lies in that particular angstrom region. Okay, it's not too far. So in angstrom region, we have only two rays. So X-rays, which you know, that lies in that 1 to 10 angstrom region. And the main condition for the diffraction of the crystal is your wavelength should be comparable to interatomic spacing. That is the main condition. So whenever someone asks you that what is the diffraction condition in terms of crystals, okay, so you have to say that the wavelength, incident wavelength, should be comparable to the interplanar spacing. Then and then only you will get a diffraction from the crystal. Now this is the timeline. As I already mentioned, the 1868 X-rays were discovered by Röntgen. In 1901, he has got first Nobel Prize in physics. And later on, as time progressed, there are a lot of discoveries in the X-rays. Right now, we have different machines which already gives you fitted data with tool refinement. I will go into that with next few slides. And then later on, the Bragg discovery, which was the main fundamental thing in order to get the pattern, in order to know about the constructive or destructive interference of the X-ray diffraction. Why XRD? As I already mentioned, to measure spacing between layers and rows of atoms, that is the same thing which I mentioned, in order to measure the interatomic spacing. Okay, interatomic placing or interplanar distance means distance between two consecutive planes. Interatomic spacing means you can say as a parameter, that is lattice parameter. What is lattice? It is the infinite number of arrangement of periodic points in imaginary space. Okay, so in real space we know that, okay, whenever you consider any unit cell, it is not like it should be separate. Okay, in reality it is in very much close to each other, but for our understanding we are considering it is in reciprocal space. So if you know the ek diagram or ek curve, okay, or the momentum, you can write as a h cross k. So where k is wave vector. Okay, so 2 pi by lambda. So if you inverse that, so in order to visualize the crystal structure, we are all considering all those things, lattice, bases, crystal structures in a reciprocal space. This is very important thing. Okay, then second thing, we can determine the orientation of a single crystal. Okay, orientation of single crystal means what? You know that any crystal consists of grains, consists of domains, and inside domains you have dipole moments. Okay, and the dipole moments per unit volume gives you the polarization. Now, if it is a single crystal, what will be there? There will be one grain and one domain. In that, all domains are aligned in a particular directions. Then, in that case, we can say a single crystal. In case of polycrystalline material, okay. In case of polycrystalline material, you have separate domains in which all dipoles are oriented in a different directions. So you might have studied about the P hysteresis curve or magnetization versus applied field curve, MH curve, okay, hysteresis curve. Most of this studied. Then to find the crystal structure of unknown material, let's say if I give any sample and if I perform the XRD, from that I am able to find the crystal structure. You know that there are 7 crystal structures starting from cubic, tetragonal, orthorhombic, rhomboedral, monoclinic, hexagonal, and trigonal. Okay, these are 7 crystal structure, and there are 14 Bravais lattices. 14 Bravais lattices. And it can measure the size, shape, internal stress of the small crystalline region. Okay, so as I mentioned, what is diffraction? It is basically in case of particle, we will get a scattering in all directions. Now, whenever it interacts with the crystal, okay, so you are supposed to get the scattered rays in a particular directions, and later on we will move to this Bragg diffraction condition in order to check the when at which point or at which angle we are supposed to get the constructive interference. Okay, so this is the X-ray diffraction. As I mentioned, it is based on the constructive interference. Constructive interference means what? Interference you might have seen in 12th also. If there are two waves which are superimposed to each other, whenever they coincide, and if the crest match with the crest, okay, or trough matches with trough, the resultant amplitude of the wave will get enhanced. Okay, in that case, we can say the constructive interference. And destructive interference, whenever your crest matches with the trough of another wave, then the resultant wave, which as you can see, that is the destructive interference. Now in this case, you have the incident beam. This is the crystalline material, and this is the diffracted beam at a particular angle. Now in this case, if my incident angle, okay, let's assume the incident angle is theta, a diffraction pattern which is recorded on the particular film, in this case, it is in 2 theta region, remember. Okay, so I will go to that X-ray pattern also, which I have taken. So you are getting the graph, final graph, which is intensity versus 2 theta, not theta. Because what you assume, now in this crystal, we don't know. Okay, let's say it has many planes, which are oriented in 1, 1, 1, 2, 2, 2 directions. Now we are assuming that whatever incident beam is there, it just scattered in this direction. Let's say if I have one plane which is in this rotation, okay, like this, just wait. so that in that case, the angle or the scattered ray which is in this direction. So in order to get that particular pattern, we are taking totally 2 theta angles so that we can get those all diffracted beams. Now this is the Bragg's law, which you might have already studied in first year or third year also in solid state physics course. Now this is the first ray which are incident. These are the atomic planes. You can see this is the first plane, this is the second plane. These are the lattice points. You can see the dots. Okay, these are the lattice points. The distance between those two lattice points is a interplanar spacing. That is small a. And the distance between two planes, you can see that it is d. Using the simple geometry, we can calculate the path difference. Let's say this is the first ray which is incident on that point and it just scattered. The second ray, if you consider this second ray, A, B, C, okay. Now you can check that it has to travel more path difference compared to the first ray. Okay, what is that extra path difference? That is AB plus BC. Now using simple geometry, I'm not going in detail of that as we already studied that. We can calculate this path difference. So AB, which look like as a d sine theta. How it comes? Your theta, this is now sine theta. We know that front side divided by hypotenuse. So AB upon d. So your AB will give the d sine theta. Same thing about BC. It will give the d sine theta. So total path difference which has to travel, it is 2d sine theta. Now in that case, n, which is the order of fringe, either it is first order, second order, lambda is the wavelength. Now in this case, depending upon the source which you are using, either it will be copper, either it will be molybdenum, the wavelength will vary, and 2d sine theta. Okay, so 2d sine theta. Now in this case, what is the limiting condition? Your maximum n lambda should be less than equal to 2d. Means what? If you substitute n lambda equal to 2d, 2d will get cancelled and sine theta equal to 1. As we know, sine theta varies maximum value from 0 to 1. So that is the limiting condition. N lambda less than equal to 2d. So that's why we are not able to use visible rays. Okay. If someone asks you why we don't get diffraction from the crystal if you pass as normal light, visible light. So that is the limiting condition according to the Bragg diffraction law. Okay. So in the other way also you can prove that. Same thing which I mentioned. I'm not going into detail of that. And the basic of crystallography, as I already mentioned, lattice, which is the infinite number of points which are in reciprocal space. Then the atom which is attached to that lattice, okay, which gives you the basis, or some in some books they have mentioned motif, MOTIF. Okay, so basis is also known as motif. In maybe Decker or Kittel, they have used that term motif. And the lattice plus basis forms a crystal structure. Now the unit cell, okay, so unit cell, Wigner's cell, you might have studied all those different phenomena. Now unit cell, which is the smallest unit, okay, which has the identical surroundings, smallest part of the unit in that particular crystal. Okay, in unit cell, you can imagine in other way on the component. If you consider the unit cell on its continuous repetition, you can generate a crystal structure. Same thing like you can imagine in a wall. Okay, so if you have a single brick, if you post on the different brick, arranging different bricks, it will create a wall. Okay, same thing about the crystal structure. If you attach the different unit cell, okay, surrounding to the particular unit cell, it will create a crystal structure. And the dimension, as I mentioned, it is 3-dimensional. So A, B, C are the axes, and alpha, beta, gamma are the lattice constant, which has to be determined by the XRD. Now, these are the 7 crystal structures which I already referred. I'm not going into all of that. Starting from the cubic to triclinic. So cubic is the most stable, having A equal to B equal to C. That is in X, Y, Z direction. It is symmetric cubic, you can say. And alpha, beta, gamma are supposed to 90. And these structures are vary. These are the parameters. And the Miller indices. Now Miller indices. So whenever I say a single crystal which is oriented in a particular direction, so I need to give it nomenclature at it is oriented in particular direction. Okay, so this is made up of series of planes, and each plane is placed with the atomic spacing. Now imagine if you have one plane and two planes. Okay, so the scattering of that particular plane, let's say if my X-rays are incident and scattered from 1 plane, and secondary X-rays which is 2 which is just below of that 1 whenever I get excited pattern, so I can write as 222 as a 2 times 111. Whatever intensity which I am supposed to get from that 222 pattern, which will be approximately double of that 111 pattern. Okay, so I'll go into that maybe in the next few slides. Now Miller indices, how to calculate? If you have the reciprocal length, let's say AB and 0, ABC, if you intercept length 1, infinity and half, you have to just take a reciprocal, take the LCM, you will get the Miller indices. Now what it suggests, that my planes are oriented in 102 directions. Now recently one question was asked in JAM exam. One of students told me that he has asked to draw bar 100 plane in that unit cell. Now whenever it consider unit cell, okay, the front plane which is 100, how to show the bar 100? Okay, means negative 100, that is bar 100. So in that case, what you need to do, you have to just shift the origin to the front. Okay, when you shift the origin to the front side for the 100 plane, you will get bar 100 plane, which is the back plane of that unit cell. Now the next D-spacing formula, if you know the HKL planes, which are oriented directions, if you know the value of A, you can calculate interplanar spacing. Now this is the standard formula for this unit cell. For orthogonal, the case is different. For tetragonal, case are different, because for tetragonal, we know that A is equal to B, not equal to C. For cubic unit cell, if you have A equal to B equal to C, you can calculate the interplanar spacing using this formula. Okay, so A naught upon H under root of H square plus K square plus L square. And for hexagonal, the formula is like this, because for hexagonal, we know that A is equal to B, not equal to C. Your alpha, beta are same, 90 degree, and gamma is 120 degree. Okay, so it's like elongated cylinder type structure. Now the instrumentation part, the production of X-rays, in that later on I will discuss about the collimators, then the monochromator, which are filters, crystal monochromator are there, and different types of detectors in order to detect those XRD. This is the production of X-ray. This is the X-ray tube. Okay, or X-ray tubes, you can say. This is the cooling water system. Nowadays, they are using this liquid nitrogen as a coolant in order to get that avoid the heat parameter. This is the copper rays. Okay, now you can see that whenever we apply the field to this filament, can you see this filament? So in that case, whenever you heat that filament, according to Joule's heating law, we know that H equal to I square RT. Whenever you heat that filament, it will emit the electrons by the process of thermionic emission. Okay, now what are the requirements of this filament? It should have a high melting point, and it should have a low work function. Low work function means what? Within less energy, it should emit the lot of number of electrons. Now whenever that electron will strikes on that particular copper atoms, now the source you can vary, it will be molybdenum or copper also. Now X-rays are generated. I will go into that process very soon. Okay, so this is the process. Now X-rays, how they are generated? So if your K shell, okay, if your incident energy electron beam, now energy incident electron beam, whatever we are getting, that is in kilo electron volt. Now if you consider the electron in K shell, okay, it is bound with nucleus by 13.6 electron volt energy. You know that hydrogen atom energy calculation, minus 13.6 by n square. If you consider this K shell atom that is in first shell, okay, I will pronounce 1, 2, 3, 4 as a KLMN shell. The first shell, which is having 13.6 energy, electron volt energy. Now, if I have to knock out that electron from that K shell, what I have to do? I have to supply energy which is greater than or equal to 13.6 electron volts. So, and we obviously have the energy incident that is in kilo electron volt. So obviously it will knock out the K shell electron, and the electron from higher shell, that is L shell, will come back to the K shell. And whenever it comes back to the K shell from higher state to lower state, it will emit some rays. And these are rays which are known as characteristic X-rays. And we can calculate its energy. Why they are named as characteristic X-ray? Because it has definite energy. As you already seen, the XRD is the fingerprint techniques. Okay, so each atom or each element have a characteristic energy, and we can calculate that also. For particular material, for second rays or for L shell, you can calculate as minus 13.6 by n square. So you can take it as a 2. So minus 13.6 by 4, it's somewhat around minus 3.4. So if you take a difference, the energy is somewhat approximately close to 10.2 electron volts. So that also you can calculate. So that is the characteristic energy. So whenever there is a transition from L shell to K shell or second state to one state, you will get a K alpha rays. Whenever there is a transition from M shell, L shell, okay, so third shell to first shell, you are supposed to get K beta rays. Obviously, the energy which you are getting from K beta rays, it will be less compared to the K alpha, as we have transition from third to first shell, and we know that with increase in this shell or with increase in the levels, the energy will get decreased, as we have minus 13.6 upon n square. So it is inversely proportional to the square of that shell number. Then the collimator, in order to get that narrow focus beam of X-rays, and they are allowed to pass through closely packed metals which are separated by a small gap. You can see that. And the collimator absorb all X-rays except narrow beam passes between the gap. So it's somewhat like blocker or filter, we can say. So it allows to pass all rays. It can block some particular rays. Then the monochromator, we know that monochromator is basically used to get that single wavelength from that source. You can see the slit entrance is there. There is a dispersion device, either it will be grating or prism. And on the exit sheet, you can see that we are allowed only pass one light or single wavelength through the sample. So this is the monochromator. Then detectors, obviously, whatever X-rays tubes, we are impeding X-rays on our crystal, and later on it will be scattered. Okay, so basically, X-ray diffraction is basically, I can say, a special type of scattering. Okay, special type of scattering from that atomic planes. So whatever X-rays which are diffracted or scattered, we have to detect those X-rays. For that, we will require some detectors. So initial days, they are used to the photographic plates in order to get that particular pattern. Then nowadays, there are most of the different device. Second is counter methods. GM tube is there, Geiger-Müller tube. Second one is proportional counter. Third one is the scintillation detector, and last one is semiconductor detectors. Now both types of depend upon the ability of X-ray to ionize that particular matter, and they are differ only in the subsequent fate of electrons which are produced by the ionizing process. I will cover a few of them which are most widely used, but nowadays whenever you go the different machines like Bruker Advance is there, Rigaku is there, they mostly use the scintillation detector. Okay, so I'll just explain the working within a short time. Now you can see that high energy photon means your X-rays are incident from this direction, and later on use the scintillator. Scintillator means what it does. It is made up of basically the photocathode materials. Okay, or it can scintillate, it can ionize in tracks, and whenever you have low energy photons, which will introduce on a photocathode material. A photocathode material, again the same principle. It has to, whenever a photon incident on it, it has to emit the electrons. Okay, now these are the focusing electrodes, and these are the diodes which you can see. Okay, this curly shell. A diode is basically a material which is made up of beryllium oxide or magnesium oxide, and obviously it should have a very low work function. Okay, low work function. Why? Because whenever that electron is incident on this, it will get multiplied. Depending upon the number of diodes, you will get enhanced. So you can see that initially we have one electronic pulse, and after let's say several diodes, 10 or 9, 12 diodes, you are supposed to get a maximum number of counts, electronic counts, and this is the photomultiplier tube. Okay, you can see that this is the photomultiplier tube. So most of this time, this is the crystal, which is the iodide crystal, sodium iodide crystal. Somewhat in some case, it is doped with the thallium, thallium, in order to get those particular electrons very shortly within a same thing. It should have a very low work function. That is the main important thing whenever you consider the photocathode material or diodes. Okay, diodes which are heavily doped, so that you will get a maximum number of electrons from that. Now the diffraction methods. Now there are diffraction methods. First one is the law diffraction method. Second one is rotating crystal, and the recent one, which is the powder method. In law diffraction patterns, there are different orientations. It is for a single crystal, and a polychromatic beam is used at a fixed angle. Inside, we can use the different rays. In other case, you can see the monochromatic source have to use monochromatic beam. Okay, like we are using in laser diffraction pattern. Now in the rotating crystal method, you can calculate lattice constant. It is again for single crystal in the monochromatic beam, and which can vary the angle starting from that 2 theta degree, 20 degree to 80 degree. You can vary it. And the most of the method nowadays which you are using, it is a powder method, which is obviously we can calculate the lattice parameter, that is A, B, and C. From that, you are able to recognize the crystal structures and the different parameters. So Ritwell refinement method is there in order to get those parameters or the strain which are generated in the material. And the monochromatic beam is used at variable angle. So this is the law method. You can see that the first experiment which used the white radiation of all possible wavelengths. Okay, white radiation obviously it consists of all rays as Wigner spectrum, and allowed to radiation, this falls on the stationary crystal. You can see that this is the crystal. Image is not a little bit clear, but I will explain that. And then crystal is diffracted X-ray beam and produces a pattern. This is the photographic film on which you can see the spots, which tells about the internal symmetry of the crystal. Now there are disadvantages of these crystals. So big crystals are required initially in that case in order to get diffraction pattern. And the crystal oriented is determined from the position of the spots. Okay, these spots can be indexed. Now again, these things you have to compare it with the JCPDS card. I will go with that in next few slides. Or Grignard charts is also used for the back reflection pattern, and the Leonard charts again used for the transmission pattern. And the Lau technique can be also used to access crystal perfection from size and shape. So this is the rough method, I can say, as it's not giving the full detailed information. Again, whatever pattern which you are getting, that will give the orientation of the plane, and this back reflections and transmission patterns which are denoted by the Grignard chart and Leonard charts. Then rotating crystal meter, you can see that this is your X-ray source. Now the single crystal is mounted with one axis normal to that particular X-rays which are saying, that is, let's say it is a copper K alpha source. And cylindrical film is placed around the sample. So whenever that X-ray beam which is falls on the crystal, obviously there will be diffraction in different directions. And as sample rotates, some set of planes normally satisfy the Bragg condition. So whenever the Bragg condition is satisfied, that is 2d sin theta equal to n lambda. Remember, that is the condition for constructive interference. 2d sin theta equal to n lambda. That is the Bragg diffraction condition. Whenever that condition satisfied, you can see a spot. Okay, or in nowadays in powder method, you can see the peak. Okay. Now this is the modern automated X-ray diffractometer nowadays which are using. This is the X-ray tube. This is the sample stage. Okay, you can see that it can vary with 2 theta angle. Okay, so you can vary this also, X-ray tube and detector also in different manners. If you have film or if you want a very small angle also at 10 degree also, you can easily calculate. I will go with this machine which you can see.
Since the early 20th century.
Okay, I will mute my mic. Can you see this, Krish?
Yes, sir.
Okay, so this is the
Yes, sir.
D8.
It is visible.
Yes, okay. So this is the D8 Brooker advanced machine which we are using, which I have used in Pune University while doing the research. Now you can see that this is the X-ray tube which I already shown you. This is the sample stage. Okay, so I just included this video so in order to get the exact idea how it look like. And this is the detector. So you can see that we can move this. Okay, or it's vary from 20 degree to 80 degree angle. As I mentioned, you can take at a low angle also, low angle XRD also possible. Okay, so let me show some parameter. This is the sample stage. Okay, so once you open this, and remember, this is not required any vacuum conditions. Okay, whenever you go for SEM, TM, it requires a vacuum. Okay, so this is the sample stage on which we are keeping a sample. Now it can vary. It will be the thin film or Yes, you can see that. Now this is moving. Okay, just wait. Okay, can you see this, Krish?
Yes, sir.
Okay.
Sir.
Okay, so this is the machine which you are using. These are the different buttons, high voltage. So initially, what you have to do, you have to set the different parameters starting from. So normal range which you are using for this 30 kilovolt, 30 kilovolt to 50 kilovolt, you can vary this range. These are the technical parameters. I'm not going in detail of that. There are the knobs. You can open these doors. Okay. Once you open this, you can. There are different sample holders. Remember, if you have liquid samples, the holder is different. For powder sample, the holder is different. For thin film, and using thin film also, you can calculate the thickness also using that Beer-Lambert's law. Okay, you can see that this left side pattern, which is showing that is the X-ray source from which you are impinging X-ray on your particular crystal, and then obviously it will be scattered and detected by the detectors. That's varying. Okay. Now you can see that the metal plate. Okay, the metal plate which is there, which is obviously the monochromator or the single slit or the, it will depend upon the source. Now if you are using the copper K alpha source as a X-ray source, if you place a nickel filter, okay, so it will block that K beta rays. If you want the monochromatic rays for K alpha, that is for copper, it is 1.54 angstrom. Okay, so these are the filters which we have to use. And these are the detectors. Now in this case, the PMT detector is there on the right side. You can see that. And the whole assembly later on, it is circulated by these coolants. So you will get that liquid nitrogen pattern. And you can see this XRD pattern. Intensity versus, you can see that K beta rays and K alpha rays. As I mentioned, K alpha should have large energy compared to the K beta rays. Now these are the source, these are the sample holders. You can see that. Now they are preparing the samples. This part is very much important. That's why I included that. So you will get have some idea about how it works. Normally, most of the institutes which are working in India, they used to this machine, that is D8 Advanced Brooker. This is somewhat magnetic sample holder which keeps the fixed sample. Once you place that sample, you have to close that door, and later on using the softwares, it will automatically get the diffraction angle, and you can also vary the current or the voltage which you are dealing with. It will depend upon the sample. If you have thin films, most of the time thin films have got X-rays at very low angle, so 8 degree or 10 degree. So it's very difficult to detect those angles, because you can imagine your crystal is placing like this and you have incident on that angle 8 degree. So you can imagine, so whatever patterns or scattering which are getting, that is difficult to detect. For larger angle you can detect easily. Now these are the parameters. I'm not going into detail of that. This is the start size. This what was showing, that is this time step. So if you want a slow scan, that is used for the Ritwell refinement. The voltage and current, now we are showing it is 40 kilovolt and 40 milliampere. Initially, once we open that, you have to set those parameters. You can see that at the bottom. Set parameters are there. So 20 kilovolt right now is there and 5 milli electron. And you have to increase in a stepwise. Okay, it's not like that you just keep 40 kilovolt and 40 milliampere and start. No, you have to, whenever you start the machine or whenever you shut down the machine, you have to take that parameter. And at the bottom, you can see the start angle is there, 10 degree, and increment. You can see that is 0.02 degree per second. Now, depending upon that increment, you can take the X-ray, the small angle diffraction pattern, and the size. Size means that is in 20 step. To start and end, you can take from 20 degree to 80 degree, and this is the scan speed, which is 1 second per stop. Okay, I will directly go to the pattern which are supposed to get. Okay, so you can see that you can move this detector from 20 degree to 80 degree. Anything you can get the parameter, it will automatically work. Okay, can you see this pattern, Krish?
Yes,
Yes,
yes.
sir.
Okay, so this is the X-ray diffraction pattern, but I am now seeing. Now you can see that right now it's not visible clearly, but around 72 degree, you are getting a sharp peak. Now, as I mentioned, this is the characteristic pattern of that particular material. Okay, this is the characteristic pattern of that particular material. So let's say for copper K alpha or copper source, if you have a copper single crystal, and it has peak are at 52.9 degree. So whenever if you take a copper crystal, you are supposed to get pure crystal. I'm saying you're supposed to get a diffraction peak. So whenever you can see these peaks, okay, at which what is happening, at which your Bragg diffraction condition is satisfied, means 2d sin theta equal to n lambda, that condition is satisfied. Whenever you see this bump, now these are the noise, I can say. Once you remove those backgrounds, you will get a clear pattern. Okay, again that peak which is somewhat around close to 40 degree. Now this is 2 theta, remember this is 2 theta, so theta will be 20 degree. So at that particular point you are supposed to get a diffraction peak. So this is the characteristic fingerprint, as I say, as we already discussed in Raman also, Raman spectroscopy. If you want to detect the elemental composition also, okay, so you can know at that particular pattern, you are supposed to get this pattern. If you have some impurities, let's say this is my pure material, and if I adopt some impurities, or like you are doing in semiconductors, so what you can do, instead of those two peaks, okay, this is the splitting of the peak, which I can see. Instead of those two peaks, you can see one more peak, which is obviously a impurity phase, which I can say. So whenever we are getting those peaks, we are comparing with the standard card, that is standard JCPDS card. I will go to that standard JCPDS card. Now these are the different parameters which we can calculate. Now whenever you take any peak, if you want to calculate the particle size or the residual strain in that material, now in this case the strain will be different. It is lattice strain, the one which you are using in elasticity chapter. Okay, that is different. A full width half maximum, in that case what you have to do, first of all, half maxima means whatever intensity you are getting, the intensity is arbitrary. Remember, if you are taken XRD today, if you are supposed to get intensity 1000, and in next day if you have performed same sample, so at that particular angle your intensity might vary. It will depend upon the atomic position, the temperature factor is there, absorption factor is there. Now whenever you halve the intensity, that is the full width half maxima, and later on if you draw a line from that point, okay, and if you draw a perpendicular on x-axis, we know it is 2 theta, that is in degree. You are supposed to get 2 theta 2 and 2 theta 1. From that you can calculate the beta value, and from that beta you are able to calculate the average crystallite size of that particular material. Average crystallite means somewhat you can say a very smallest individual crystal. Okay, smallest individual crystals, which is known as a crystallite size. Now there are strains, different parameter. If there is no strain, you can see that the diffraction line is there. If you have uniform strain, then peak modes and no shape changes. If you have non-uniform strains, okay, if you have non-uniform strain, obviously the shift weight will broaden. And if you have different samples, now for single crystal, we know that we are supposed to get a only sharp one peak. Okay. In polycrystal, we are supposed to get different peaks because we have different domains which are oriented in different directions. Now this is the JCPDS card which I am telling you. Now this is the standard card. Okay, let's come back to this first, then I will go back to this. Now this is the X-ray pattern of BaTiO3 material. BaTiO3, we know this is the perovskite material. When I say perovskite, any material which is having general formula AbO3. Now in this case, A atomic site, that is the Ba. At B site you have Ti and O3 is there. Now in this case, you can see there are different planes which are indexed starting from 100, 110, 111. You can see the splitting 002 and 200. That is the characteristic fingerprint for the tetragonal structure. That is characteristic thing for the tetragonal structure. You can see 002. So in this case, A is equal to B, not equal to C. Okay. So in particular materials, if you consider, again, this is the rough technique, I can say. You have to perform the tool requirement in order to get exact parameters. But roughly, I can say this is the tetragonal structure. So BaTiO3 is obviously tetragonal structures. In that case, you have your oxygen is elongated in Z directions. In that case, what I can predict, I can see the maximum intensity of 110. The intensity you can see referred is at arbitrary unit. It is not angstrom unit, it is arbitrary unit. So my X-ray intensity can vary depending upon the sample. If it is powder, if it is a pellet, the intensity will get different. Still, roughly what I can say, intensity or number of planes, 110 planes in my crystals are maximum. Is the maximum possible orientation in my BaTiO3 material, which is in 110 direction. Okay. Now there are different techniques nowadays they are using in order to texture the sample and in order to increase the particular intensity. Okay, means there's texturing and a lot of research is right now going on there in order to make the cost-effective material so that we can get a single crystal. Now in single crystal, what you are supposed to get? Only one peak, single peak. Only one peak you are supposed to get. This is polycrystalline material. Means what? This material, you have grains, you have domains, and domains are oriented in different directions, either in 100, 111, 210, but the maximum possible orientation, it is in 110 direction. So whenever I get this XRD pattern, what I need to do, I have to compare with the standard JCPDS card. What is JCPDS card? It is Joint Committee on Powder Diffraction Standards. It was proposed in 1969. Later on, it was replaced by ICDF card. Okay, so International Center for Diffraction Data. This is the site which you can go. You can refer this link. From that, you can get all types of spectra whenever you synthesize material. Now, in this case, NaCl is there. Okay, I just mentioned all those parameters. So one is the file number. So once you know the file number, you can get that data easily. And the three strongest line, you can see that 2.82, 1.99, 1.63. Now in this case, D has given. And whatever pattern which you have got, that is intensity versus 2 theta. Okay. Now 2.8 to 100 means what? It has the maximum intensity. You can see that. And it has indication 200 plane. Sorry. So whenever we get this 2.0821 or 101 plane at a particular angle, I can directly index as a 200. Then these are the parameters, this radiation of the source which are using, that is K alpha, copper K alpha, having wavelength 1.54 angstrom. Then this nickel filter is used, cutoff wavelength is there. And these are the references, okay, 5 number reference from which they have taken this data, which is Swanson, Fuat, NBC Circular. Okay, this was the reference journal from which they have got this data. Now the structure, symmetric cubic. Now FM3M, this was the space group. This was the space group. And these are the Pilatus parameter. A, B, A. In this case, they have just mentioned A. This is the density. Then 7th parameter, which is the optical and other data. I'm not going in detail of that. And the 8th one, which is the data on diffraction pattern. So X-ray diffraction, which was taken at room temperature, that is 20 degrees Celsius. Merrick index, which is the reference number, I can again say. And this is the group. These are the technical things. And this is the quality of data, which is star. structure name. Okay, so most of the time nowadays you are getting intensity versus 2 theta pattern. Okay, so whenever you say the 2 theta 50 or 31.9, so if you can just directly compare, and 31.9 you can directly index the peak. But most of the time nowadays the Riga code machine is there, which will give direct fitting of those all patterns, which will directly index your XRD. Okay, and this is the fingerprint technique. So once you compare your this data with the standard one, if it matches well with this, now what I can say, whatever sample which I have synthesized, it is having pure form. Okay, it is having tetragonal structures. Okay, and it has no impurity phases there. If there is one additional peak, let's say at this 35 degree, okay, if I'm supposed to get the additional peak, then what I can say, whatever sample which are synthesized, that is not in pure form, there is additional one peak. That may be due to the oxidation of some materials. If you're using the bismuth or any material, we know that they are volatile. We are supposed to get the additional peak once you center the sample at higher temperature. Then these are the applications from that what I mentioned. The structure of crystals, the polymer characterization also you can do. The lattice strain. Now the strain which you can calculate, if you got this scattering angle, and as we have calculated the beta, that is FWHM, from that you are easy to calculate the lattice strain using Williamson-Hall plot. Okay, using Williamson-Hall plot, that is WH plot, also nodes in the research field. So from that you can calculate the lattice strain and average crystallite size. In particle size determination, there are different methods and there are different applications. So the main application, whenever I say, whenever you go to the research, whenever you synthesize any sample, you have to first check XRD. If it is well matches with the standard card, then and then you can proceed with different characterizations, SEM, TM, dielectric measurements, any measurements you can do. First of all thing, you have to check whatever samples which are synthesized, whether it is in pure form or not. Okay, if it is in pure form, then I have to go to next. If it is not in pure form, I have to make again sample. Okay, till I will get this clear XRD pattern. You can see that there is no background in this case. Okay, background is removed. So at that particular pattern, you are supposed to get a peak, and at that particular, whenever you are getting peak, the Bragg diffraction condition is satisfied. In this case, angle might vary. This is 31 point something, this is 38 degree. Okay, so it will be different. Now limitations, any machines which has limitation, obviously, as we are not using the vacuum for the particular material. The homogeneous and single phase material is best identification as unknown. Now if there are some materials, let's say if you synthesize any different material, now some materials are not in that JCPDS dictionary still yet. Okay, if you make some compositions or if you make some substitution, like in that case BA-TiO3. Okay, if I make, let's say BA 0.8 CA 0.2 TiO3, so what I've done, BA I have taken as a 0.8 mole, Ca, that is a calcium, at the 0.2 TiO3. So in that case still data is not updated. But what we are suppose, if I replacing 0.2 calcium with barium, I am supposed to get the same XRD pattern. What will be change will be there? Whenever I substitute the calcium at BA side, some lattice strain should be generated. So I can expect some shift in the XRD pattern. Either it will be on left side or right side, depending upon the ionic size which I am placing. Means if it is, let's say for barium, it is ionic radius 1.3 angstrom. And if you are substituting the calcium, okay, which is enclosing this barium 1.4 angstrom, if you a value is increase, the sine theta will also going to be decrease. As we know, 2d sine theta and lambda, d is proportional to a, so they are inversely proportional. So what I am supposed to get, let's say at this point I'm getting 31.8 degree, I am just able to see, or I'm just able to predict that shift is just little bit shifted, 31.72 or something. Okay, it's will be really small. So that is the detection limit. 2% of samples require 10th of gram material, which must be grounded into powder for particular material. And for unit cell determination, indexing of patterns, non-isometric crystal system is complicated. Okay, so some materials or some biological samples are also there, which requires whatever X-ray source energy which you are impeding, which will should not react with the X-rays. Okay, it should not react with the X-rays. Okay, The peak overlap may occur and worsens high angle reflections. So at higher angle, as I mentioned, higher angle and lower angle also, we are facing some problems till late, because let's say if you are crystal and if your incline angle of the X-ray beam at 5 degree or 10 degree, you're not supposed to get the maximum pattern at the detector. Okay, for higher angle it is no problem, and for much more higher angles greater than 90 degree, so again there is same problem. So these are demerits, I can say, or but nowadays they also overcome, trying to researchers also trying overcome to those problems. And this is the conclusion which I conclude with talk. Due to this time limit, actually I'm not able to cover all those topics. For all materials, including metals, minerals, plastics, pharmaceuticals, semiconductors, XRD apparatus provide highly accurate tools for non-destructive analysis. Remember, this is non-destructive technique. It will not affect on your sample in any case. And there is no sample preparation requirement is there. For other techniques, you have to prepare the sample. Means you have, let's say for TM, you have to make a film in that particular thickness, 1 to 100 nanometer. Then and then you are getting this TM pattern. For scanning electron microscopy, you have to coat your sample. And for different biological samples, there are different conditions. You have to use KBR, you have to mix with KBR. There are a lot of parameters. I'm not going into detail of that. And the diffraction patterns are supported by extensive range of application software. So the prominent companies or the softwares which are nowadays we are using, that is D8 Advanced Brooker, which is from Germany, and Rigaku, 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 which is again the Japanese company, which are most dominant companies in this XRD field. And again, this is useful to characterize material for the phase analysis, lattice parameter determination, strain determination, texture orientation analysis, and the phase transformation also you can calculate. So whenever you see, let's say this is BA203 material, now it is splitting at this 45 degree. Okay, now we know that BA203 is ferroelectric material, and it has Curie temperature at 120 degrees Celsius. Means what? After 120 degrees Celsius, it will become a paraelectric material. Curie temperature means ferro to paraelectric conversion. At paraelectric, the structure will be at cubic. So if I take that XRD at 130 degrees Celsius, I can take XRD with temperature also. Remember, at low temperature also, starting from 5K. Yesterday, Sati sir has shown us there are different types of instruments which are in DA indoor. So you can take XRD from 5K to any temperature, higher temperature. So if I take that XRD at 130 degrees Celsius, I'm supposed to get a single peak like this, 111. I'm supposed to get single peak. Okay. So if you take the readings with respect to temperature, extra diffraction, let's say this is the room temperature, 30 degree, 50 degree, 60 degree. So we can see that with increasing temperature, the shift will merge into the single peak. So from that also you are able to predict the phase transformation temperature or Curie temperature. Okay. So these are the things. I think I have covered most of the. These are the references from which I have taken, and this is the author stream presentation from which I have taken that video. And thank you for all of you for your kind attention.
Thank you.
Yes, sir. Well,
Okay, now as we've concluded the lecture, the floor is open for questions to be put on the chat box. So we will be sparing 1 to 2 minutes for any questions that have to be put up.
Omkar sir?
yes, sir.
Yeah, at the outset, I would say it's an excellent lecture on the XRD research instrument I ever heard. Right? It's really all credit goes to you.
Thanks.
So definitely this is an informative session for our students, right? Because you started from the very basic to the
Hello,
Sound is not there.
sir. Your voice is not audible.
If nobody
Okay.
is having any question, I will ask one question.
Yes, sir.
So
Just let us wait, if some students are asking, because, concluding the lecture without interaction or without question, I think,
Yes, sir.
uh, you know, Harish
Sir,
or any student from
Omkar sir,
Yes,
what
sir.
was that ritual? Ritual you mentioned.
Okay, sir. Ritual deferment, basically that is the technique. Okay, let's me go back to the slide. Okay, so this was the X-ray pattern which I'm getting. Now, whenever you consider the ferret samples, Ratinder must know about this. Ferret samples have a lot of background noise. Let's say if I make a cobalt ferret, so in order to remove that background noise, and ritual deferment is a basically technique in which you have the PCR file. Okay, that is the extension PCR file, which we can get from that ICDD pattern, standard pattern. You have to again same thing. You have to fit your data with the standard one. Okay, so once you fit your data with the standard one, you are supposed to get a lot of parameters, lattice parameters, angles, the density of your particular material. Also, you can calculate theoretical density.
Sir, yesterday one student had asked about the density function. Does it related to that whatever density function you are mentioning right now?
Uh, yes, sir. Actually, we can calculate that. There are theoretical models, so you can make that PA203 model theoretically also, and from that you can calculate. In density functional theory is basically used to calculate the band gap. Now, in this case, BA203 is a insulating materials. Obviously, we know that it is the dielectric material, which is obviously insulator, which is mostly used in the capacitor applications, capacitor storage.
Okay, thank you, sir.
Yes, sir. Yes, Rati, sir.
Omkar, so many peaks are there, and each peak represent family of familiar indices. So in between, you said that the this is a orthogonal. So for the orthogonal, you don't just require this HKL. You requires the orientation also. So
Yes, sir.
how do you predict about the orientation from the given peak? Because they simply gives you the reciprocal of the intercept axis of the plane.
Yes, sir.
I hope
So,
you must have got
yes,
my
sir.
question.
Clear, clear. So most of the time, let's say if I have taken XRD, okay, if I made this BA203 material sample, I'm getting this XRD. What I will do, I just compare this XRD pattern with the standard one. Okay, let's say now this is NaCl, this is a different one. But if I compare that X-ray pattern of that with JCPDS card of BA203, from that I can easily get indexing HKL planes. Okay, so these are the indexing planes, and if you get the HKL values, you can obviously calculate the D value, intermediate spacing. You know this lattice parameter, and using ritual refinement again, as my sir mentioned, that is the most important technique. Nowadays, people are used to whatever patterns which are synthesized, they are comparing with the theoretical models so that you can exactly get those ABC lattice parameters. And once you compare with that, you can easily calculate the orientations. You will get all parameters in the ritual refinement, all parameters.
Okay, thank you.
Yes, sir. Welcome. Any other questions, students?
Uh, Hello, Omkar sir.
Yes, sir.
If nobody is asking, shall I ask something?
Yes, sir. Sure, sir.
Okay, students, please ask something because you have studied this particular subject right from the 12th standard, if I'm not wrong, XRD, okay, and planes and all that. Sir, there is one question in my mind
Yes, sir.
that you said that theoretical prediction is possible if we are making some combination of material. Like I'm going for some weight combination, and then I can put it in the that software, and I could go for the ritual right now. It is
Yes, sir.
like a iteration basis right now. It goes on
Yes, sir.
compiling again and again, and once the iterations get over, right, we could get very good right theoretical predictions of all lattice parameters. So is it possible for our students if they start at the early age like FYBC, SYBC, and if they focus, because these softwares are plenty available on the net. Even I
Yes, sir.
tried it. Yeah, even I tried it. So is it possible for our SY students, TY students to go for
Yes, sir.
something?
It is possible. Basically, the theoretical model which you have to use, There is one software which is Quantum Expresso, which is now, I think it is paid software, but I will try to get a license copy. I have that in with my research lab. So Quantum Expresso is there. Okay, so those who are interested, they can search. Okay, or they can get a trial copy. I think it's for 7 days. And ritual requirement, a foolproof suit is also free software. Foolproof suit, which is again important parameter. And X-ray, don't know exactly the name right now. Foolproof suit is most of the parameter. And Win PCR, WN PCR, Win PCR 2.0. There are a lot of versions. Win PCR 2.0 also we can use.
Okay, hello students. Onkar sir had supplied very important information to you. Right? It's not possible for you to sometimes do the practical things. But while sitting at home, if your PC is of good quality, right, laptop, PC, okay, whatever instrument, you can still go ahead at your own pace, right? So sir is typing that, and I did try that, right? Even though I do not have the knowledge of these particular combinations, but I did try it. It needs some patience, and you can work out some theoretical model. You can start with a simple model like NaCl, right? The information about the NaCl is available, and you can verify how it works, right? You can gain a lot of information. So those who are aiming for chemistry and physics, right? Okay, so it's really suitable for them. So take my advice, and Omkar sir is there, Rathi sir is there. They are the experts in this particular field, especially ferrites and ferroelectrics. Okay, so nobody's asking any question. Krish, you can take over.
Okay, I'd like to thank Onkar sir again for a very perceptive explanation. I have sure gained a lot of insights from this topic. I've taken a lot of things. This avenue, this platform has given us so much more than our regular syllabus. And Onkar sir sure has crossed the limits to actually giving us facilities which we may never get, at this level. So it has been really insightful, sir. Thank you for giving us these insights, and I'm sure all of us have taken from this lecture. So I'd like to thank sir personally on a personal note too.
Thank you. Thank you, Krish.
Okay, now we move on with our day. With the next flow of events, we have our second expert speaker who would be joining us shortly.
Okay, Devendra sir. Hello. Who is doing recording? You can take a break here.
Okay, sir.
Recording break. So the next time, Krish, what is the next time?